an element. So we said that the mass spectrometer, when we use it, we can determine the number of isotopes and the relative isotopic masses of each isotope, and from which we can calculate the relative atomic mass of the element. And we said that, of course, we have to know about the monoatomic elements, but we also said that we are having two diatomic elements that we are going to study their mass spectrum, diatomic elements. Last time we talked about chlorine, which is a diatomic element, and today, inshallah, we are going to take bromine. Now, as we said, in case of chlorine, bromine has two isotopes. We have bromine 79, and we have two isotopes for bromine, bromine 79 and bromine 81. And from these two isotopes, the bromine element is formed. And this bromine element can either be formed by the bonding of two bromine isotopes of 79, or else it can be formed from bromine 79 and the other bromine atom should be 81, or that both bromine atoms are from the isotope which is 81. So here we have bromine, the diatomic element. It could be formed either of these three ways, either from two atoms of the bromine isotope, which is 79, or one of them is 79, the other is 81, which is the second isotope of bromine, or both bromine atoms are of the isotope 81. Now, if the bromine molecule is formed from these two bromine atoms, then our bromine molecule will have a molecular mass of, when we add 79 to plus 79, it makes 158. If both bromine atoms, one of them is 79 and the other is bromine 81, we get the bromine molecule, which is 160. And if both bromine atoms were of the isotope 81, then we get the bromine 162. So either we get bromine 158 or bromine 160 or bromine 162. And as we said last time, when this element is bombarded with highly energetic electrons, then an electron will be ejected from this molecule, just like as what we did in chlorine, and bromine Br2 positive is formed. And of course, this bromine 2 positive is either the bromine 158 or the 160 or the 162. That's why when we look at the mass spectrum of the diatomic element bromine Br2, we will find that we have here, we draw the mass over charge ratio, and here we have the percentage abundance. We said that percentage abundance means its percentage in nature. And then we will get three peaks. One for bromine 158, the second for bromine, of course, having positive ions, because whenever we place anything in the mass spectrometer and it is bombarded with electrons, the electrons will eject an electron outside the element and we get the Br2 positive. So all of these are Br2 positives, and we get these three isotopes. One of them is at 158, the other is at 160, and the third is at 162. This is at 158. This is at 160. This is at 162. We said that this is the mass of each isotope because the charge is usually positive 1. So we get three peaks. We call these peaks, and these peaks are in the ratio of 1 to 2 to 1. Not as like when we talked about chlorine. When we had chlorine, if you remember, in chlorine element, we had three peaks also for the three isotopes of Cl2 positive, but they were in the ratio 9 to 6 to 1. And we, of course, I explained to you why the ratio is 9 to 6 to 1. So this is for chlorine. But for bromine, we have the more ratio 1 to 2 to 1. We have to know these ratios. Okay, we have to know why the ratio of chlorine is 9 to 6 to 1 and why the ratio of bromine is 1 to 2 to 1. Of course, if you do not remember what we said about chlorine last time, I can repeat the explanation. But let's start here with bromine. Now, bromine has two isotopes, the bromine 79 and the bromine 81. And we said that in case of bromine, they are present in the ratio of 50% to 50%, which means that they are in the ratio of 1 to 1. And the total ratio is 2. So here we have the ratio between bromine 79 to bromine 81 is 1 to 1 because they are present 50% each. Not like in case of chlorine. Chlorine 35 was 75% and chlorine 37 was 25%. But here both percentage is the same, 50% and 50%, which means that the ratio between, or the moles, or the ratio between bromine 79 to bromine 81 is 1 to 1, which means that the total is 2. Now, as we did last time in case of bromine, we are going to do the same in case of bromine. We say that for the first Br2 positive having this mass 158, it comes from bromine 79 and another bromine 79. The probability that a bromine, in the first case, the probability that the bromine is 79 and the other is also 79, we say that the ratio here is 1 to 1 and the total ratio is half, is 2. Then this means that the probability that this bromine 79 to be formed is half. And for the other bromine is also half. We divide 1 divided by 2. And so half times half makes 1 over 4. For the second probability, that we have either the first bromine to be 79 and the second to be 81. So for the first probability that this bromine is of the isotope 79 will be half 1 over 2. And also for the second, the bromine 81, it will also be 1 over 2, the same probability. But as we said last time, that the first atom could be 79 and the second could be 81, or else we have the first atom of the isotope 81 and the second 79. So also we get half times half, and this makes 2 over 4. And for the last probability that both bromine atoms forming the Br2 molecule, they are both of the isotope 81. So the probability that the first one is 81 is 1 over 2, which is half, times the probability that the second one would be 81 is also 1 over 2. And so if we multiply them together, we get 1 over 4. So the ratios of Br2 158 to Br2 160 to Br2 162 would be 1 over 4 to 2 over 4 to 1 over 4. And so we cancel the 4 and we get the ratio 1 to 2 to 1. That's why the peaks here are in this ratio, which is 1 to 2 to 1. Okay, understand, or do you have any question? Do you want me to repeat anything? Yes. Okay, Mavi, thank you so much. Yeah, does anyone have any question? We said that after bromine forms and after it forms the Br2 positive, it will still be bombarded more by electrons. And at that time, the bromine will be fragmented or broken down into Br and Br. We have Br2. And when it is collided or bombarded with this sea of electrons, then it will be fragmented or it will be broken down into the two bromine atoms. One of them could be the 79 and the other could be the 81, which means that in the mass spectrum, we are going to get two extra peaks, one of them at 79 and the other at 81, 79 and 81. And as you see here that the ratio 79 and 81, you will see that the ratio is 1 to 1 because they are present in nature in 50% each. So the ratio would be 50% to 50%, which means 1 to 1, and we get these two peaks in the same ratio. Okay, you understand? Do you have any question? You remember what we said about chlorine last time, or should I repeat it? Do you understand the chlorine? When we said that chlorine is formed from, also, we have two isotopes of chlorine, chlorine 35 and chlorine 37, but they are present in the ratio of 3 to 1 instead of 1 to 1 in case of bromine. So the total ratio is 4. We said that the chlorine molecule is either formed from these two isotopes, which is the chlorine 35, to form the Cl270, having the positive charge, because all the ions present in the mass spectrometer are present as positive charge, or the second probability that one of them is 35 and the other 37, and so we get the Cl2, which is 72. So here we get a peak at 70, another peak at 72, and the last one, when both isotopes are of the chlorine 37, we get the Cl2, which is 74. So we get this peak. And we said that the ratio is 9 to 6 to 1, depending on the probability of the formation of these ions. We said that for the first type, which is chlorine 70, it is formed from chlorine 35, and the other atom is also chlorine 35. Each of one of them has the probability of 3 divided by 4. So we say 3 over 4 times 3 over 4, and this makes 9 over 16. For the second probability, the two atoms could be 35 and 37. 35 has a probability of 3 over 4, and the probability of 37 is 1 over 4. Okay, and then we said that maybe the first chlorine was the one that has the 37 and the second has 35. So we say plus 1 over 4 times 3 over 4, and this makes 6 over 16. And the last probability is that both chlorine atoms are of the 37 isotope. So we say 1 over 4 times 1 over 4, and this makes 1 over 16, which means that the ratios are 9 over 16 to 6 over 16 to 1 over 16. We cancel the 16, and the more ratio will be 9 to 6 to 1. And then after chlorine positive is formed, when it is bombarded by more electrons, it will be fragmented or broken down into chlorine atoms of these two isotopes, which is the 35 and the 37. But here they are in the more ratio of 3 to 1. One of them is 35 and the other is 37. Okay. Do you have any question for the mass spectrum of elements? Yes, yes, Mavi.
I just want to ask, why are they even converted into ions in the first place in the mass spectrometer?
Because they are bombarded with electrons. We said that in the mass spectrometer, at the beginning, you introduce your element from here. You introduce it to a high heating so that it turns into vapor, and then the vapor is bombarded with highly energetic electrons coming out from an electron gun.
Oh yeah, I get that part, but the question is why do they want to turn them into ions in the first place? Is there a specific reason?
In order to accelerate them within the mass spectrometer, because if they are neutral atoms, they cannot be accelerated within the mass spectrometer. You remember that here they place here two electric plates, electric fields here. And the electric field will not work if the atoms were in the form of neutral atoms. They have to be in positive ions so that to be attracted and repelled by the electric field. Once attracted, if they are present in the form of positive ions, then they will be attracted to the negative plate and then repelled by the positive plate. And this will force them to accelerate within the mass spectrometer.
Okay, thank you so much.
You're welcome. Okay. Do you have any question about, yes, do you have any question about the mass spectrometer and how do we get the different isotopes of any element? How do we calculate the relative atomic mass of any element, including the diatomic elements, which are chlorine and bromine. Yes, Rodina, do you have any question?
Yeah, Miss, for the peaks for 35 and 37, can you explain that part again, please?
When chlorine molecule now is formed, the chlorine in the form Cl2 positive, it is subjected to more bombardment with more electrons. And when electrons strike the chlorine molecule, it will be fragmented or broken down into two chlorine atoms. Because the chlorine molecule has a bond in between the two chlorine atoms, it will be broken by the bombardment of the chlorine molecule by electrons, or the bromine molecule by electrons. Okay?
Okay, thank you.
You're welcome. Now, if we take any molecule, of course, we studied about elements, but now if I have a molecule, and this is going to be explained much more in Unit 2, but now you have to know about what happens if I have a molecule, because in the last exam, they asked about it. So, of course, we are going to study this in very more details in Unit 2, but here we have to know what happens if I have an organic molecule. What happens to the organic molecule? The same thing will happen. We are going to subject our organic molecule to the collision with highly energetic beam of electrons. And the electrons, when they strike the molecule, they are going to eject an electron outside this molecule, forming a positive ion. What do we get in the mass spectrum? When we have a molecule, we will not get isotopes, but this is the molecule. This is a molecule. And so also the mass spectrum is about percentage abundance, is drawn the plot, percentage abundance against mass over charge ratio, the same as what we did in case of elements. But here, the last peak that appears here will be called the molecular ion peak. This last peak will be called the molecular ion peak, which we call it Mn positive. This is called the molecular ion peak, from which we can get the molecular mass of the molecule. We get from here the MR of the molecule. The last peak in the mass spectrum of a molecule is, we call it the molecular ion peak, and it will give us the molar mass of the molecule. If you remember when we were talking about the empirical formula and the molecular formula, they usually give us in the problem, they usually give us the MR of the molecule. They get it from here. They get it from the mass spectrum of the molecule. When we draw the percentage abundance against mass over charge, the last peak in a molecule is called the molecular ion peak, from where we can get the MR of the molecule. Okay? Now, what happens when this molecule is formed? Now it forms a positive ion, and then this positive ion will be subjected to the bombardment with more highly energetic beam of electrons, and this ion is going to be broken down or fragmented into smaller positive ions, and each of these positive ions will give a peak in the mass spectrum of the molecule. So the peaks here in case of the molecule are not isotopes, but they are the fragmented parts of the molecule when it is subjected to the bombardment by more number of electrons. We get here different peaks. Each peak represents part of the molecule that is broken, part of the molecule which is broken. So every one of them will have a molecular mass, which is the molecular mass of this small peak. What do we mean by small peaks? We are going to talk about this in Unit 2. We are going to study it or explain it in more details. But all you have to know here is that in case of a molecule, the last peak, we call it the molecular ion peak. It's Mn positive, and it gives us the molecular mass of the molecule. And all the peaks that are going to be obtained here in the mass spectrometer is about the fragments or the fragmentation of this molecule to very smaller molecules. Each fragment gives a peak here with its molecular mass. Now, yes? Yes, they are not elements, they are fragments. I will show you how, but you are not now, yani at this part, you are not going to be asked about this. But for example, if I have something like, for example, ethanol, if you have ethanol, Yamavi, okay? If you have ethanol, so what is fragmentation of ethanol? At the beginning, you get the positive ion by bombarding the ethanol with electrons. You get the ethanol having the positive charge, and you will get this peak at the molecular mass of this ethanol. So ethanol has 2 carbon atoms, it has 6 hydrogens, it has an oxygen. So altogether we have 46. So you get here a peak at 46. This peak, which we got at 46, is the molecular mass of ethanol, okay? And then ethanol is subjected to the bombardment with more number of electrons. So what is it going to be done? Here, the molecule is going to be fragmented. Fragmented means it's going to be broken. It can be broken into CH3 positive, or it can be broken into CH2OH positive. So you get a peak at CH3 means 15 if you count. If you add 12 plus 3, it makes 15. And here you get 12 plus 3 hydrogens plus 1 oxygen. So altogether it's 31. So you get a peak at 15 and you get a peak at 31. So every peak here corresponds to a fragment of the molecule. And as I told you, we are going to study this in more details, but I only wanted to show you what is meant by fragmentation. It means that you are going to break the molecule into smaller fragments. And each fragment has a certain molecular mass. You are going to obtain it in your spectrum. Okay? Understand this? Okay. Thank you so much. Now, sometimes you get here a peak, a very, very small peak here. If I'm going to draw it using the blue color, sometimes you get here a very, very small peak after the molecular ion peak by only 1 unit. For example, here for ethanol, we had the molecular ion peak at 46. You get this very small peak at 47. We call this peak the M+1 peak. What is this M+1 peak? We know that in organic compounds, all the organic compounds are formed from carbon. And we know that carbon has 2 isotopes in our atmosphere, which is the carbon-12 and the carbon-13. But if you look at the percentages of carbon-12 to carbon-13, you will find that carbon-12 is about 99%, and that carbon-13 is only about 1%, which means that when an organic molecule forms, all of the carbon atoms could be of the isotope 12, and at that case, you get only the molecular ion peak. But if only one atom in your molecule is carbon-13 of this isotope, not the carbon-12, you will get this M+1 peak. It means that if you calculate here the molecular mass, you found it to be 46. But maybe one of these carbon atoms was carbon-13, so you will get 47 instead of 36. You will count 12 plus 13 plus 6 plus 16. Okay? So you get what we call the M+1 peak beside the molecular ion peak. This is because of the presence of an atom of carbon-13, of the isotope carbon-13. Okay? Understand, or do you have any question? Type. Okay. Now, if we look here, this is the mass spectrum of the element bromine, which is the diatomic element that we talked about, bromine. It has 2 isotopes, 79 and 81, and this is the peaks that corresponds to the Br2 positive, whether both of them are of the first isotope 79, or both of them of the isotope which is 81, or both isotopes are present in the bromine molecule. Okay, so as you see here, this is a question that comes in exam, and you have to know about it, to explain about it. Now we come to the second part of this chapter, which is the atomic orbitals and electronic configurations. Now, of course, we know that all atoms consist of a positive nucleus in the middle, This is the electronic configuration or quantum shells. And electronic configuration. Of course, we have studied before that any atom consists of a positive nucleus around which we have different energy shells that we call them quantum shells. And the name quantum means that they do not move, they are present at fixed positions. This is what we call quantum. Quantum means that they are present at fixed positions. Now, for example, if I have a molecule like this, an atom like this one, we have 3 shells, for example. The first shell is n equal 1, the second shell is n equals 2, and the third shell is n equals 3. Now, when instruments were old, they detected that an atom consists of a positive nucleus in the middle around which we have these fixed energy shells at which electrons, of course, we are going to fill, and they are going to fill in a certain order as we are going to take. Now, when instruments became more advanced, they found that these shells are not only single shells as appear here in this drawing, but we will see that the first shell is the same. It does not divide. Shells are going to be divided into subshells. But the first shell is not divided, but the second shell is going to be divided into 2. They found that the second shell was divided into 2. But these two subshells are very close to energy to each other. And the third shell was divided into 3 subshells, but they were very close to each other. That's why in the old instruments, they couldn't see these shells. They couldn't determine these shells because they were very, very close to each other. We'll see here that the third shell is divided into 3 different subshells with very close energies. And as they are very close, they appear to be as if they are only one shell in old instruments. And the fourth is divided into 4 shells, 4 subshells. So this was the shell number 1. This is the shell number 2, and this is the shell number 3. But as I told you, as modern instruments were formed, they knew that each shell is more divided into what we call subshells. Exactly like when I say that, for example, I'm wearing glasses and I was standing up far away from my friend, and then my friend put 2 fingers like that, and she told me, how many fingers are these? And I was not wearing my glasses, and from a long distance, I say it's only 1 finger, because I cannot see that there are 2 fingers that are very close together from a far distance. And when I was not wearing my glasses, I saw that there is only 1 finger, not 2 fingers. But when I wear my glasses and I come nearer, I will find that they are 2 fingers, but they are very close to each other. They are just touching each other. That's why from a big distance, I thought that they are only 1 finger. That's what happened here in shells, where electrons are moving. Electrons are moving in shells. And at the beginning, when the instruments were old, they saw that the first shell consists of only 1 shell, the second is also 1 shell, and the third, the fourth, all of the shells are only 1 shell. But when the instruments became modern, they became more advanced, they have seen that the first shell is not divided, but the second shell is divided into 2 subshells. We call this division, we call it subshells. And the third shell is divided into 3 subshells. The fourth is divided into 4 subshells, and so on. Now, what if I have an electron here and I want to describe its position? I want to describe this electron. I will say that this electron is present in the second shell and in the second subshell. If I want to describe this electron, I will say that it is present in the third shell in the third subshell. Or else if it is here, I will say that it is present in the third shell in the first subshell. And of course, this will make confusion when we call shells and subshells in numbers. This will cause confusion. That's why they said, okay, now for the subshells, we are going to give them letters and not numbers. So if we have the first shell, we are going to call it, since we have only one shell, one subshell, we are going to call it S. And since the second shell consists of two subshells, we are going to call one of them S, and we are going to call the second P. So this will be S, and this will be P, this will be S. Okay, and for the third shell, since it has three subshells, then we are going to call one of them S, the second P, and the third D. And for the fourth shell, it is divided into four subshells. We are going to call them S, P, D, and F. Okay, we don't have more than that. We don't have more than the F. Okay, now they said, okay, but also there will be confusion because we have an S from the first shell, we have an S from the second shell, we have an S from the third, we have P from the second, we have P from the fourth and the third shells as well. So there will be confusion as well. So they said, no, we are going to call this one 1S, which means that it comes from shell number 1, and it is the first shell to be filled by electrons. And the second one, we are going to call these two subshells 2S and 2P, which means that they come from the second shell and from the first subshell and from the second subshell. And for the third shell, we are going to call them 3S, 3P, 3D. And for the fourth shell, they are going to be called 4S, 4P, 4D, and 4F. Okay? Understand till now, or do you have any question? Okay. Now, when electrons are moving, they do not move in orbitals like this. They do not move straight forward like this. No, when they are moving around the nucleus, they also move in wave motion, and they have different shapes at which they are present. What do we mean by shapes? Now, we say that for every subshell, the electrons are not present in a definite place. We say that the probability of finding the probability of finding an electron in a space volume, in a particular space volume, is donated by an orbital. So we will say that when electrons are present in the 1s subshell, there is not only one position at which this electron should be found. No, there is a space volume at which the electrons in the 1s is present. What do we mean by a space volume? It means that if I have an electron that is present in an s orbital, it means that it will have a spherical shape. The s orbital have a spherical shape. What do we mean by this? It means that if I have an electron that is present in the s subshell or the s orbital, it doesn't have a certain place to be found at, but we can find it here, or 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 here, or there, or here, which means that if we collected all the probabilities at which I can find an electron in the s orbital, when they collect all the positions at which this electron could be found, it will take a spherical shape. I will repeat, we said that electrons could be found either in the s subshells or the p subshells or the d or the f subshells. It could be found at any place. But is the 1s position, it's only one specific position? No. If an electron is present in a subshell which is called S, the first one in each level, we will find that there is a probability of finding this electron, and the probability of finding the electron is within this space volume. an electron, for example, of hydrogen atoms, one of them could be found here, one of them could be found here, one of them could be found there. If we collect all the positions at which this electron is present, is a spherical shape, and we say that the s orbital has a spherical shape, and it is only one orbital. So we say that every subshell is more divided into what we call orbitals, and the orbital for 1s is only one orbital, which is the probability of finding the electrons in a 1s or in an s. All s orbitals are only a certain one space volume in space. But if the electron is present in the p subshell, if it is present in the p subshell, there are three possible probabilities for this electron to be present. We call them px, py, pz. If we have a p subshell, then the probability of finding the electron in a p subshell will have three different probabilities. We call them px, py, and pz. What is the shape of these px, py, pz? Any p subshell has what we call a dumbbell shape. A dumbbell shape, which, what do we mean by dumbbell shape? It means this shape. This is called dumbbell shape. Okay. We have three different probabilities for the p subshell, not one probability like in the case of s orbital to be spherical in shape. No. In case of the p subshell, we have three different probabilities. Either this dumbbell shape lies along the x-axis. You know, of course, that we have three axes in the 3 dimensions. We have the x-axis, we have the y-axis, and we have the z-axis. And the three axes are perpendicular to each other. Maybe you have heard about this thing from mathematics. You will see that in case of the 3 dimensions, we draw the 3 dimensions, which are the x-axis, the y-axis, and the z-axis. All these axes are perpendicular to each other. Of course, we have this also in case of the s orbital, but since the s orbital is spherical, so it doesn't matter that we draw the x and y and z, because all of them will lie within this sphere. All of them will be included in this sphere. But in case of the p subshell, we have 3p orbitals, which is the px, which lies along the x-axis. We have a py, which lies along the y-axis, and we have a pz orbital, which lies along the z-axis. So we have 3p orbitals. What do we mean by orbitals? If I have an electron in this p subshell, it could be present in any of these volume of spaces. This px, the electron, which is present in the p subshell, could be present within this volume of space. It could be present here, or here, or there, or there, or there, in every of these parts, or it can be present in the py at any place here, or it can be present at any place here. So the orbitals are the probability of finding an electron. They are not like the shells. They are not like the subshells. They are the probability of finding an electron in space. Understand what I mean, or shall I repeat this? You understand, or is it hard for you? Just we want to know that here, in case of the s subshell, it has only one orbital, which is the spherical shape orbital. And if we have a p subshell, you cannot visualize it. Okay, you should not visualize it because it's very complicated. You cannot visualize it, Yamavi. It's very complicated, really. Okay, Rodina, thank you so much. You cannot visualize it because it's beyond our vision, Yamavi. It's beyond our vision, really. It means when you see, for example, in any place drawing the atom, they draw it. They draw things like that, isn't it? What does this mean? You have seen this structure before, or this shape before for an atom? Yes. Why do they draw it like this? Because the electrons could be moving in this direction, or in that direction, or in this direction. So these are the directions where you could find the p orbitals. The p orbitals represent the probability of finding an electron. They are not roads at which electrons are moving. They are not roads. You understand me? They are just imaginary. They are just imaginary shapes at which the probability of finding electron could be there. I say that if a p subshell is present and there is an electron present in this p subshell, this means that there is a probability that I can find this electron in this place, or that place, or that place, or this, or this, or that, or here. It could be present here, or it could be present here. So it could be present if I collect all these together, but it will be very complicated. You will see that we have 3 p orbitals, one here, one there, and one here. So you will find that the electrons, when they are rotating around the nucleus in p subshells, they will take either of these probabilities to find the electrons. Some electrons are moving in this direction, others are moving in that direction, thirds are moving in that direction. That's why when they draw the atom, they draw it in this way, because we have different probabilities at which electrons can move. So all you have to know here, if it's very complicated for you, that shells are divided into subshells that we call them S, P, D, and F. And then the S orbital is only just one orbital, which is the S orbital. The S is one orbital. You will find that the P has 3 orbitals. The 3 orbitals are, we are going to call them Px, Py, and Pz. For n equals 3, we have أهلا يا عمر. Okay, I allowed you recording, يا عمر. عليكم السلام, أهلا بيك. I allowed you recording. Okay, so if we have the P subshell, the P subshell is divided into 3 orbitals, which we call them Px, Py, and Pz. For n equals 3, we have the S orbital. We have the P subshell, which is divided into 3 p orbitals. Okay, and we have the D subshell. The D subshell is divided into 5 d orbitals, 1, 2, 3, 4, 5. So here we say that we have, for the S subshell, we have only 1 orbital. For the second subshell, we have 2s, it has only 1 orbital, but the 2p has 3 orbitals. The 3s has only 1 orbital, the 3p has 3 orbitals, the 3d has 5 orbitals, and the f has 7 orbitals. You see, all the numbers are odd numbers: 1, 2, 3, 4, 5, 6, and 7. We have 7 orbitals. If you want to imagine this, you can if you want to understand about the atom, you can think about a house. If we have a house, if I have a house, and this house is built so that it's like an inverted pyramid like this, we are going to imagine that the atom is like a pyramid, but it's an inverted pyramid like this. And in any house, we have the first floor, we have the second floor, we have the third floor, we have the fourth, and so on, isn't it? So this house is the atom. And the floors of this house are the shells. The first floor, n equal 1, the second floor, n equals 2, the third floor, n equals 3, and so on. Okay, now each floor consists of apartments, isn't it? In each floor, we have apartments. The first floor has only 1 apartment, which we are going to call it 1s. This is the first shell or the first floor consists of one apartment. We are going to call it 1S. But the second floor has two apartments. One of them is called 2S and the other is called 2P. Okay. The third floor has three apartments. We are going to call them 3S, 3P, and 3D. Okay. The fourth, we are going to call them 4S, 4P, 4D, and 4F, and so on. We are not going to have more than the 4F. Okay. So we imagine that the atom is like a house and that the shells are the floors and the apartments are the subshells. The apartments are the subshells, that each floor consists of more than one or a number of apartments. These are the subshells. Now, inside each apartment, we have rooms, isn't it? Inside the apartments, we have rooms. These rooms are the orbitals. In each apartment, we have rooms. The rooms corresponds to the orbitals. Okay? Understand now? Can you imagine it now, Yamavi?
Yeah, that's a very helpful analogy.
Okay. Now, each room cannot take inside it except two persons. In each room, maximum, there should be two persons present only. It cannot accept more than two persons inside each room. That's what we are going to say about the orbitals, that each orbital cannot accommodate more than two electrons. So if you can understand the atom in that way, that the atom represents a house, that the shells represent the floors in an atom, the subshells are the apartments inside each shell, and then inside each apartment, we have rooms which corresponds to the orbitals. Each room cannot accommodate more than two persons, and here also, in case of the orbitals, each orbital can take two electrons maximum. It cannot take more than two electrons. So if each orbital, this box represents an orbital, if each orbital can take two electrons, so for the first shell, which has only one orbital, which is the 1s orbital, it will take only two electrons maximum. It can take one electron or it can take two electrons maximum. For the second shell, the 2s can take maximum two electrons, but for the 2p, as it is divided into three orbitals, and each orbital can take two electrons, so maximum it can take six electrons. If it takes two here, two here, two here, this means that we have 6 electrons. Okay. For the third shell, it has three subshells. The S can take 2 electrons. The P can take 6 electrons because it consists of 3 orbitals. The D can take 10 electrons because it has 5 D orbitals. For the fourth shell, the S takes 2 electrons. The P takes 6 electrons. The D takes 10 electrons, and the F will take 14 electrons because it has 7 D orbitals. So if you look here at what we took before, that the number of electrons inside each shell is given by the formula that the number of electrons equal 2n squared. We count or we calculate the number of electrons in each shell, where n is the number of shells. N is the number of shells. So in order to find out the number of electrons in each shell, we give this formula that number of electrons equal 2n squared, where n is the number of the shell. So if we have the first shell, n equal 1, so 1 squared makes 1 times 2, we have 2 electrons. If we look at the second shell, then 2 to the power 2 makes 4 times 2, it should take 8 electrons. When you were in O level, you say 2, 2, 8, 8, isn't it? But it's not 8, 8, it should be 8, 18. The third shell can hold up till 18 electrons. If you put here 3 squared, it makes 9 times 2 makes 18 electrons. 2 plus 6 plus 10, they are 18 electrons. If you put here n equal 4 for the fourth shell, n squared, 4 squared makes 16, times 2 makes 32. If you add 2 plus 6 plus 10 plus 14, it makes 32. So this is how electrons are distributed. They are distributed within shells, within subshells, and within orbitals. And as we said, that each orbital can take maximum 2 electrons. And the shapes, when they ask you about the shape of the s orbital, all you have to do is to draw a circle. What does this circle mean? It means the probability of finding an electron in a certain volume of space in the s orbital. It means that you can find the electron in any place inside this circle. But just when they ask you to draw an s orbital, you just draw a circle like this. Okay? When they ask you to draw the p shape, you draw a dumbbell shape, either along the x-axis or the y or the z. We have the 3 of them. But when they ask you to draw the p subshell, draw one of them only. You don't have to draw the 3. And also the p subshell, which has the 3 p orbitals, it represents the probability of finding an electron in the p, the position of finding the electron in the p subshell. It could be in any place here or there, or it could be in any place here or there, or here and there. These drawings are the probability of finding an electron. The position of electron cannot be determined precisely, cannot be determined accurately, but we say that it is within this area. Its place is within this area. We cannot determine exactly where. Understand me? Or do you have any question? Do you have any question, please? Thank you, Mavi. Do you have any question? Type. How are electrons filled within the atom? Do they go anywhere they would like? Will they go to any shell, to any subshell, or to any orbital they like? Of course not. There are always rules. Now, what is this rule? The rule says that the electrons should fill the shells from the least electrons. That's what we call the electronic configuration. It means the arrangement of the electrons. The electrons fill the shell or the subshell or the orbital with the lowest energy first, and then by the highest, yani it goes to the highest and the higher to the highest. Now, what is this order of energy shells? What is the order of energy shells by which electrons are going to fill? We will see that if this is the positive nucleus, we are going to draw shells just like a line. So of course, around the nucleus, we have the energy shells are circular, but we are going to draw them as lines, just to show the order of the energy of each shell and of each subshell. Now, if this is the nucleus, so the nearest shell to the nucleus is the 1s. The second shell is the 2s. The third shell is the 2p. Why don't we have a 1p? Because as we said here, that the first shell is not divided. It's only one subshell, which is 1s. We said that the first is not divided. It's only 1s. The second is divided to 2. The third is divided to 3. The fourth is divided to 4. So that's what we are going to say here, that if we want the order of the subshells, the first shell is the first subshell is the 1s, the second is the 2s, the 2p. Now after 2p, we have 3s, we have 3p, and then we should have 3d. But the rule says that the 4s is going to be filled first before the 3d. This is an exception. Of course, the 4s and the 3d are two subshells that are overlapping together. They are overlapping together. That's why the electrons will fill the 4s before the 3d. And we are not going to take it in more details, just to know that. You have to know that this part is explained or is studied in the university on level 3. So it's very complicated. It's not a simple one. It's not a simple thing to study now. Just you have to know that when electrons fill in an atom, they fill the 1s subshell first, followed by the second, followed by the third, by the fourth, by the fifth. Here, after the 3p, we don't have 3d. We have 4s as a lower energy before the 3d, and then comes the 4p, and then comes afterwards, after the 3d, 4p, we come to the 5s. We will not reach this one. We reach up till 4p. Okay, so electrons are going to fill by order. They have to fill the 1s first before filling the 2s. When the 1s is finished with electrons, it cannot take more electrons than the remaining electrons will go to the 2s. When the 2s is filled, then is full, then the electrons will fill the 2p. After the 2p, of course, as we said, that the 1s should be filled maximum by 2 electrons. Of course, we are going to take now examples of electronic configuration. The 2s is going to be filled by 2 electrons. Whenever we have a p, we said that the p has 3 rooms or 3 orbitals. Each orbital is filled by 2 electrons, so maximum it can take up till 6 electrons. The 3s will be filled by maximum 2 electrons, and so on. The 3p by 6 electrons, 4s by 2, and then the 3d should be filled by 10 electrons because the 3d has 5 orbitals, and each orbital is filled by 2 electrons, as we are going to see, and then followed by the 4p and the 5s by 2 electrons, and so on. Okay, you understand till now? Of course, I'm going to give you a lot of examples, but do you understand till here? Yes, thank you, Mavi. Okay, now let's have examples. Let's leave this in order to find how electrons are filled. For example, if I have I have hydrogen atom. The hydrogen atom contains only 1 electron. So where will this electron go? If I have a hydrogen atom, where will this electron go? It will enter the atom. Where? At which shell of this, or at which subshell? Yes, excellent, Ya Abdurrahman. Yes, excellent, Yamag. It will fill the 1s first. So the entering electron in the hydrogen atom should go to the 1s. It cannot go to the 2s, cannot go to the 3p, cannot go to the 3d. No, it is obliged to fill the 1s first. And since it's only 1 electron, we are going to write 1s1. The 1s is the subshell fill, and the 1 here at the upper here part means that we have 1 electron. Because hydrogen has only 1 electron, we say 1s1. Then we come to helium. Helium has 2 electrons because it has 2 protons, it has 2 electrons. Where will they go? Yes. Yes, excellent, Yamavi. They also will enter the 1s because the 1s should be filled by 2 electrons before getting to a higher energy shell. We have to fill the 1s first, and the 1s is filled by 2 electrons. So if we have these 2 electrons, they should also go in the 1s. So if I draw these things in box, this electronic configuration, we call this electronic configuration. If I draw it in boxes, I have an electron here in the 1s for hydrogen. For helium, I have 2 electrons. We are going to draw them with 2 arrows. Of course, I'm going to tell you what the arrows mean. We have here, we have only 1 electron. We draw it as an arrow, as an upright arrow. But when we have 2 electrons, we have to draw 2 opposite arrows. I'm drawing them as half arrows, but you can draw them like this. It's okay. Either we draw them as I did or like this. Both are correct. Now we come to lithium. Lithium has 3 electrons. Now, when the electrons in lithium fill the atom, they start to fill in the atom. They, of course, will start by filling the 1s. So the 1s is going to be filled by its 2 electrons. But the third electron cannot enter the 1s because the maximum number of electrons that can fill the 1s is 2. So where will this third electron go? Yes. Excellent, ya Mavi. It should go, yes, ya Abdurrahman. Excellent. It will go to the second shell, which is the 2s. When the 1s is filled by its 2 electrons, then the third electron should go to the 2s. So we say 1s2, 2s1, which means that we have 2 electrons in the 1s and we have 1 electron in the 2s. Okay, this is the way to express the electrons in what we call boxes. Sometimes they ask you to draw in boxes. They will tell you, write the electronic configuration in boxes. Now, if I have beryllium, beryllium has 4 electrons. So the first 2 will go to the 1s. And the second 2 will go to the 2s because the 2s can take 2 electrons. Yes. Yes, Ya Omar. But it cannot go to the 2p except when we have more than 4 electrons, Ya Omar, isn't it? Because here in beryllium, we have only 4 electrons. Isn't it, Ya Omar? We have only 4 electrons. So the first 2 will fill the 1s. The 1s can take 2 electrons. And then the 2 remaining electrons will go to the second shell, which is the 2s. Understand me? Okay, Omar? So we have to fill the 1s by 2 electrons and the 2s by 2 electrons. Okay, thank you so much. Now, after that comes boron. Now, boron, as Omar said, now at the beginning, the first 2 electrons are going to fill in the 1s by 2 electrons. The 1s can take 2 electrons, so they fill these 2 electrons in the 1s. Then the second 2 electrons are going to fill the 2s by 2 electrons. But now we filled only 4. You see here, if you count, if you add these, they are 4 electrons. Still, we have another electron, which is the 5th electron, and the 1s and the 2s are now filled. So Omar said we are going to fill the 2p. Yes, excellent. If we fill the first subshell by 2 electrons, the second by the second 2 electrons, then the 5th electron should go to the 2p subshell. But we have to fill them in order. You cannot put an electron in the 2p without and leaving the 1s and the 2s empty. No, you have to fill them first before you fill the 2p. Okay? So here boron has 1s2. When we write the electronic configuration, we say 1s2, 2s2, 2p1. Okay, now when we draw them in boxes, so the 1s has 2 electrons, the 2s has only 2 electrons, each one is only 1 orbital. But when we draw the p orbital, p orbitals, we have to draw them 3 p orbitals because the p subshell is divided into 3 p orbitals. Okay, so this electron is going to be filled here. Can it be filled here or here? Yes, it can. But yani, by convention, we stated that when we fill the first electron, we put it in the first box. But you can put it here or you can put it there. All of them have the same energy. You can put it anywhere. It's not wrong. But by convention, we say that this is the place where we place our first electron in the p subshell. Now, after boron comes the carbon. The carbon has 6 electrons. So we say 1s2, 2s2, and then 2p2. As long as we have a p subshell, it can be filled by 6 electrons. Now we just filled it by 2 electrons in carbon. If I draw this p orbital, I draw it like that. Now we have 2 electrons in the p subshell. Will we put them both together in the same place, or we put every one of them in a different place? The p subshell is divided into 3 p orbitals. As we see here, we have 3 boxes. When we had in boron just 1 electron, we put this electron here, and as I told you, we can put it here or there or wherever. But when we have 2 electrons in the carbon atom in the p subshell, so we have 2 probabilities. Either we put both electrons in the same orbital, or we place every electron in a different orbital. Now, scientists said that in order to place the electrons in a p subshell, we cannot put two electrons in the same orbital at the beginning. We have to put the first electron in an orbital and the second electron in another orbital. Why this is this is a better way to express the electrons more than that? Yes, excellent, Yamag, excellent. Because electrons have similar charge. We know that the electron has a negative charge. And if we are placing two electrons in the same orbital, repulsion will take place between them. We say that like charges repel and unlike charges attract. So if these two electrons are present here, in case of carbon, if they are present here in the same orbital, they will repel each other. Just like when two persons are living in the same room, they quarrel a lot. Why? Because one of them wants to read and he wants lights up, and the other wants to sleep and he wants the light to be off. One of them wants to open the window, the other wants to close the window, isn't it? So they will quarrel. That's what happens with electrons when they are placed in the same orbital, the same room, they repel each other. So they will be, it's better for the electrons to be placed, each electron in a different orbital than the other. Okay, so when we draw in boxes the electrons of the p subshell in case of the carbon atom, we should draw the electrons, every one of them, to be separated away from the other, one here and the other there. Of course, I didn't draw the 1s and the 2s because I was just showing the p. Not every atom I'm going to draw all the orbitals, so just the 2p here, only to show you that these two electrons, every one of them should fill a different orbital than the other. And when we come to nitrogen 7, it will be, can you tell me, Rodaina, can you tell me the electronic configuration of the nitrogen?
1s2.
Yes.
2s2.
Excellent.
2p, and then
yes, excellent, Yamavi. Yes.
2p3, sorry.
Yes, excellent. 2p3, excellent, Eurodine. When you count the number of electrons here, you will find that 2 plus 2 makes 4, 4 plus 3 makes 7. So these are the 7 electrons that are present in nitrogen. Excellent, Rodaina. Abdurrahman, can you give me the electronic configuration of oxygen 8?
1s2.
Yes, excellent.
2s2.
Excellent.
2p4.
Excellent. So if we look at nitrogen, excellent, Abdurrahman, if we look at nitrogen, it has 3 electrons in the p subshell. And since the p subshell contains 3 orbitals, so we are going to place every electron separately in each orbital. But when we come to oxygen, it has 4 electrons, not only 3. So we are going to say 1, 2, 3. Now, where will the 4th electron go? We are obliged to put it together with another electron in the same orbital, because the p subshell can take up to 6 electrons. Every 2 electrons in an orbital, it can take so. Yes, at the beginning, when we have more rooms, more empty rooms, we say that we should fill every electron in a different room than the other. But now we are obliged to put 2 electrons in the same orbital because we have 4. We have filled the p orbitals 1, 1, 1, and the 4th electron should be filled in the same orbital with another electron. Okay, understand? Okay, Mavi, can you tell me the electronic configuration of fluorine 9?
1s2, 2s2, and 2p5.
Excellent. 1s2, 2s2, 2p5. Because now there's a 5th electron that should be added. And here, as long as we are at the p subshell, it can accommodate up till 6 electrons. And so these are only 5. So we have 3 rooms. We put 1, 2, 3, 4, and then 5. Okay. And now we come to the last element or the last atom in this period, which is neon 10. Can you tell me the electronic configuration, ya Hiba, of neon?
1s2, 2s2,
Yes.
and 2p6.
Excellent. It's 1s2, 2s2, 2p6. So if you look here, excellent, ya Hiba, if we look at this p subshell, we will find that we have 6 electrons, 1, 2, 3, 4, 5, 6. Now the p orbital or the p subshell is completely blocked. It took all the electrons it can. So Mawadda, if I have the next element, which is sodium 11, of course, I'm going to start it in a new page, but I wanted to leave this arrangement for you. Mawadda, what will be the electronic configuration of sodium 11?
1s2,
Yes.
2s2,
Excellent.
2p4, and 3s2.
No, the p orbital must be filled by how many electrons?
2p5.
2p6. The p subshell can take up till 6 electrons.
Oh, I mean 3s1.
Yes, then 3s1. Excellent.
Yeah.
So excellent, Mawadda. You have to write 1s2, 2s2, 2p6, and then 3s1. Understand? So now we started a new shell. Now, if you look at these elements, you will find that hydrogen and helium are present in number 1, means the first shell. This number means the number of the shell. Shell n equals 1, isn't it? For both, the number of shell is 1. And we know, Fallon, that hydrogen and helium in the periodic table are present in the first shell. If you look at these, starting from lithium till neon, you will find them to fill the second shell. You see, this is the last shell to be filled. We take, of course, for lithium, we have only 2s. For beryllium, we have 2s. For boron, we have 2s, 2p. We collect the two or the numbers that are similar. The last numbers means the last shells to be filled. So here we have 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, 2s2, 2p6. We mean that we are still present in the second shell. The last electrons feed in 2s, 2p, or 2 only, 2s only, 2s, 2p. The number 2 means that we are still present in the second period. You will see that if you have periodic table in front of you now, you will see that lithium till neon are all present in the second period. That's why they fill the second number 2 maximum. You will also see that the number of electrons that are present in the last shell represents the number of the group. Of course, we know that hydrogen and helium are exceptions. But if you look here at lithium, lithium is present in the first group. You see that it ends up with S1. It means that here, this is the last shell to be filled. It's the second period, but it's in a group number 1 because we have only 1 electron in the last shell. If we look at beryllium, we'll see that this is the second shell to be filled, and it fills in S2. It means that it is present in group 2. If we look at boron, it is filling the second shell because we have number 2 here below or beside the S and the P, we have 2. But if we count the number of electrons, 2 plus 1 makes 3. This makes boron present at group 3. So the number of electrons that are present in the last shell will give us the number of the group. If I look at oxygen, I have here 2 plus 4 makes 6. And oxygen is present in group 6. It has 8 electrons, but it is present in group 6 because the last shell is filled by 6 electrons, isn't it? And neon is present in group 8, or we call it now group 0, but they were present at the beginning in group 8 because if we count 2 plus 6 makes 8. This is the last shell to be filled. Now look at sodium. The last shell in sodium is the 3s, like what Mawadda said. They fill in the 3s. It means that now we started a new shell. I want all of you to have periodic tables in front of you. If you look at these periodic tables, you will see that sodium is present in the third period. It's not beside neon. It is below lithium. you will see that it fills a new shell, which is the third shell, but it has only one electron in the S, like lithium. It has only one electron in the last shell, which means that it belongs to the first group, just like lithium, group number 1. Okay. Omar, can you give me the electronic configuration of magnesium? Yes, Omar, can you give me the electronic configuration of magnesium?
1s1 or 1s2,
Excellent.
2s2,
Excellent.
2p6,
Excellent.
3s6,
3s.
6 miss.
Why 6?
Mhm.
The s orbital cannot be filled by more than 2 electrons, isn't it?
S2, is it 2?
Yes, and if you count these numbers, count 2
that's
plus
12.
2, they are 10, and then there is left 2 electrons, so they are going to fill the 3s by 2 electrons. The S subshell cannot be filled except by 2 electrons maximum. Yes, excellent, Yamar. Okay, ya Omar,
Okay,
the S subshell cannot be filled by more than 2 electrons. And if you count here, 2 plus 2 makes 4, plus 6 makes 10, so we are left with 2 more electrons to fill in the 3s. Okay. And also you will find that magnesium is present in the third period. Here we have 3, means the third period, and it is in group 2 since we have only 2 electrons in the third period. Understand, or do you have any question?
all good, miss.
Okay, thank you, Omar. Huh?
Thank-
Do you have any question? Type. Let's take aluminium. Aluminium 13. It will be 1s2, 2s2, 2p6, 3s2. If you count these numbers, you will find them to be 12. Then there is an electron left. Where shall we put this electron? Mavi, where shall we put this electron? After the 3s?
In the 3p
Yes.
subshell.
Yes, excellent. In the 3, yes, ya Abdurrahman, excellent. It will start to fill the 3p subshell, but still it is present in the third period. Hiba, what about silicon 14?
Miss.
Yes, Hiba.
1s2,
Yes.
s2,
2s2.
2p6,
Excellent.
2s2.
3s2.
I mean 3s2. Yeah, sorry.
Yes.
And p2.
And
3p2.
excellent. 3p2. So this is the last shell. It's in the third period. And if you count here, 2 plus 2 makes 4, which means that silicon is present in group 4. Yes, it lies below carbon in group 4. Abdurrahman, phosphorus.
1s2,
Yes.
2s2,
Yes.
2p6,
Excellent.
3s2,
Yes.
3p3.
Excellent. It means that phosphorus is present in the third period and in group 5, and so on. We are going to continue sulfur. So it's 1s2, 2s2, 2p6, 3s2, 3p4. It means that it is present in the third period and in the sixth group. After sulfur, we have chlorine. It ends up with 3s2, 3p5. As long as the p subshell did not complete its 6 electrons, we have to fill it until it completes its 8 electrons. So argon will be 1s2, 2s2, 2p6, 3s2, 3p6. And now we finished. The p subshell could be filled maximum by 6 electrons, and this means that argon is the last element in this period. Then comes potassium, which is 19. Then we say 1s2, 2s2, 2p6, 3s2, 3p6, and then what, Rodina? After 3p6, do you remember what we are going to fill?
After 3p6, you fill the 4s subshell because the 4s
Excellent.
is lower than 3d.
Yes, excellent, Rodina. Excellent, Abdurrahman. After the 3p, we are going to fill the 4s. We are not going to fill 3d. We said that the rule says that we fill the 4s first before the 3d. So after we completed the p subshell by its 6 electrons, then the shell that is going to be filled after the 3p is the 4s. This is our rule, to fill the 4s before the 3d. And that's why here we are going to fill this 4s by 1 electron. Okay, and then after potassium comes calcium, which is 20, and we say 1s2, 2s2, 2p6, 3s2, 3p6, and then we fill the 4s by 2 electrons, and we didn't fill the 3d yet. If you look at your periodic table, you will see that after calcium comes the row of the transition metals. Can you see them, or shall I show you? I'm going to show you at Google. You see here, can you see the periodic table? Can you see it or not yet? Do you see the periodic table?
Yeah.
Okay. Now
Yes,
you will
ma'am.
see that, thank you so much. We will see that we stopped at calcium. Calcium has 20 electrons. Of course, this is the number of protons, which is equal to the number of electrons in a neutral atom. So after calcium, we will start this group, starting from scandium up till zinc. We call this the transition elements. Of course, we didn't have them in period 1, nor in period 2, nor in period 3. They started in period 4, when we filled the electronic configuration of potassium and then calcium, after which we come to scandium. Because as we have seen that calcium has 2 electrons in its 4s. Now the 4s completed its number of electrons. So after the 4s, we have to fill the 3d subshell, starting by the transition metals, starting by scandium. So if we continue here our electronic configuration, we will see that scandium comes after calcium. It has 21 electrons, and so its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. We are going to write the 3d, but we are going to leave it empty. We are going to fill the 2 electrons for the 4s. Now we fill 20 electrons. We are left with 1 electron that should be filled, so it will fill the 3d. So always we fill the 4s first and then the 3d. Why did I write the 3d before the 4s? This is as I told you, there are things that we do it by convention. By convention means that all the scientists agreed to do this electronic configuration, to write the 3d after the 3p, but not fill it before the 4s. The 4s should be filled first, and then the 3d will be filled second. But we write it before the 4s. This is a convention way. This is a way that we have a system done by what we call the IUPAC. It is an organization, International Union of Pure and Applied Chemistry. They told us what to do, so that everyone in the whole world, when you get any reference in front of you, you can understand it, because all of us talk by the same speech, which is the chemistry. So they stated that when we fill the electronic configuration, yes, we are going to fill the 4s first by its 2 electrons and then fill the 3d, but on writing, we write the 3d before the 4s. What if anybody wrote the 3d after the 4s? It will not be wrong. They will also say, okay, this is correct. But as I told you, if you open any reference, you will find them writing the 3d before the 4s. But if you write it after the 4s, it's okay. Halas? Understand? So scandium is the first element in the transition metals. Of course, I'm saying transition metals, although it is not a transition metal. If anyone will continue A2, you will see that scandium is not a transition metal, but it's we call this the D block elements because it filled in the D subshell, but it's not a transition metal. This is only an information for you that scandium is not a transition metal, but it is within the D block elements. Now, after scandium comes titanium, which is 22, which is 1s2, 2s2, 2p6, 3s2, 3p6, 3d. I'm going to leave it empty. I'm going to fill the 4s first by 2 electrons. Now we have 20 electrons, and then put the 2 here on the 3d. Okay, we fill the 4s first by its 2 electrons, and then I complete the 22 electrons by 2 electrons in the 3d. After that comes vanadium, 23. We say 1s2, 2s2, 2p6, 3s2, 3p6, 3d. I leave it empty. I fill 4s first by its 2 electrons, and then we have 3 electrons left. We put them on the 3d. Now we come to our first exception, which is the chromium. We have 2 exceptions only. We come to the chromium, which is 24. So when we fill the electronic configuration of chromium, it should be 1s2, 2s2, 2p6, 3s2, 3p6. I leave the 3d empty. I write 4s2, and then write here 4. But if we write the electronic configuration of chromium in this way, it will be wrong. Why? Because we have a rule. What does this rule say? It says that if a subshell is half filled or completely filled, this gives it greater stability. This gives it greater stability. Okay, what do we mean by this? Now, if you look here at the 3D subshell, it is filled by, the 3D has 5 orbitals. Okay, 1, 2, 3, 4, 5, and we have next to it the 4s. The 3D has 4 electrons, 1, 2, 3, 4, and the 4s has 2 electrons. And our rule says that if a subshell is half filled or completely filled, this will give it greater stability. So if we look here at the 3D subshell, we find that there was only 1 electron left. If we had this electron, then the 3D would be half filled. What do we mean by half filled? We know that the 3D subshell can be filled by how many electrons, Ya Omar? The 3D.
By 2?
Yeah. The 3, not orbital, the 3D, yes, Yamavi, excellent. The 3D subshell, all these, we call it the 3D subshell. Yes, Yahiba, excellent. Every orbital, Ya Omar, is filled by 2 electrons, isn't it? Okay, it has 5 orbitals, but each orbital can be filled by 2 electrons, as we said. كنا بنقول كل أوضة تاخد 2, isn't it? Every orbital can take 2 electrons, isn't it, Ya Omar? We have 5 orbitals, and then 5 rooms, but each room can take up till 2 electrons, isn't it? So how many electrons altogether can be taken by the 3D? What do you think, Ya Omar? Yes, excellent. It can take 10 electrons. The 3D can take 10 electrons. So if it takes 10 electrons, we say that it is completely filled. If it takes 10 electrons, then it is completely filled. And if it takes 5 electrons only, we call it half filled. You understand now all what is half filled and what is completely filled? The 3D subshell has 5 d orbitals. 5, 1, 2, 3, 4, 5 orbitals. Each orbital can take 2 electrons. So altogether, the 3D can take up till 10 electrons. If it takes 10 electrons, we say that it is completely filled. If it takes only 5, we say that it is half filled. And the rule says that if a subshell is half filled or completely filled, this makes it more stable. And this means that if we look at chromium, it has only one electron left, so that it will be half filled and will be more stable. So what will the chromium do? It says that it looks at the 4s and it says that me and you are one thing. The 3D and the 4s are overlapping together. They represent only one subshell because they are overlapping. So it says, please give me an electron to fill my last orbital, and you will also be half filled and will have greater stability. Yani L4s will not, it will not be harmed by giving its electron to the 3D, because it will be half filled and the 3D at that time will be half filled, and both of them will be more stable than when the 3D was only containing 4 electrons. Understand? So here, when we write the electronic configuration of chromium, it should be chromium, which is 24, we say 1s2, 2s2, 2p6, 3s2, 3p6, and then we come to the D, we say 3d5, 4s1. Okay, this is the correct electronic configuration of chromium. If you write it 3d4, 4s2, it will be wrong. You have to write it 3d5, 4s1, so that it becomes more stable. Understand, or shall I repeat? Do you have any question? Okay, now after chromium comes manganese, 25. It will be filled as usual, 1s2, 2s2. Who can tell me? Yes, Hiba? We don't have except 2 exceptions, Hiba. We have only chromium and another exception, which will be copper. We don't have except these 2.
Oh, all right,
Okay.
thank you so much.
Okay. So for manganese, Mawadda, can you fill the electronic configuration of manganese? Can you complete this? 1s2, 2s2, and then?
Okay. 1s1, 2s2,
1s2, 2s2, yes.
2p6,
Yes, excellent.
3s2,
Yes,
3p6,
excellent.
4s2,
Bravo, excellent.
and 3d. Wait, wait, I need to count. Sorry.
Okay, yes, I know. I know that all of you must use the calculator. You cannot count without the calculator. So do it, please. My sons are like you, Yan.
So 3d5.
Yes, excellent. It should be yes, Mavi. Yes, excellent. So yes, excellent, Mawadda. It will be 3d5. Excellent. So here the chromium was the only exception up till now. Okay, Rodaina, can you fill iron 26?
1s2,
Yes,
2s2,
excellent.
2p6,
Yes,
3s2,
yes,
3p6,
excellent.
3d10.
No,
No,
we said
4,
after the 3p we fill.
4s2.
Yes, Mavi, excellent, excellent, Rodaina, 4s2, and then how many electrons are left?
1 second, miss.
Okay.
3d6.
Yes, excellent. 3d6, excellent, bravo. So this is the electronic configuration of iron. Now we come after iron, we have cobalt. Cobalt will fill, yes, Rodaina.
Can you explain why chromium is an exception again?
It's an exception because we have a rule that says if a subshell is half filled or completely filled, this will give the element greater stability. So if you look at chromium, it fills 4 electrons in the 3D. It has only 1 electron left. If it filled the 3D by 5 electrons, it will be more stable than its position here when we have 3d4. If you have 3d5, it will be more stable than the 3d4, isn't it?
Yeah, okay.
It's a rule. It's a rule. We have to, yani, we have to use this rule. Okay. Now, after iron, we have chromium. Sorry, we have cobalt. After iron, we have cobalt 27, which is 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 4s2, 3d7. Then after cobalt, we have nickel 28, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Yes, excellent, Mark. Now we come to the second exception, which is the copper. The copper 29, it is 1s2, 2s2, 2p6, 3s2, 3p6. We leave the 3d empty, we fill the 4s first, then we have 20 electrons. So the ninth electron will be present here in the 3d subshell. And if we write the electronic configuration in this way, it will be wrong. Because we said, our rule said that if we have a subshell that is half filled or completely filled, this gives it greater stability, isn't it? So Abdurrahman, what is the correct electronic configuration for copper?
Place in 4D.
Yes, but tell me
For,
the full electronic
okay.
configuration.
1s2,
Yes,
2s2,
excellent,
2p6,
excellent.
3s2,
Yes,
3p6.
yes,
Leave 3D empty.
yes.
4s2.
Okay, I wrote 4s2 above, but now
Oh.
we said that this is incorrect. So what are we going to do?
Place electrons from 3D into 4D. 4p.
From four, you mean from 4s?
4s, sorry.
Yes, excellent. Yes, excellent, Yamavi. We are going to take an electron from 4s just as we did in chromium, isn't it? You have 9 electrons. Let me show it to you in a new page. In case of copper, we have 29 electrons. Yes, Yehiba, excellent, bravo. We have 1s2, 2s2, 2p6, 3s2, 3p6. If we write like usual, we will write 4s2 and 3d9. We will see that in the 3d subshell, we have 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And in the 4s, we have 2 electrons. And our rule says that if a subshell is half filled or completely filled, this gives it greater stability. Now we see that copper has only 1 electron left. If it had this electron, it would be completely filled in the D subshell, and it will give it greater stability. So if you write the electronic configuration in this way, it will be wrong. So what will the copper do? It will borrow an electron from the 4s to itself. Why? To complete the D subshell by 10 electrons. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It completed its D subshell to be completely filled, and the 4s has an electron. It means half filled, so it's okay for it. And this will make copper more stable. So when we write the electronic configuration for copper, we say 1s2, 2s2, 2p6, 3s2, 3p6. Then we say 3d10, 4s1, because at the beginning we wrote it, we started with the 4s, but when we found that the d orbital needs only 1 more electron to be completely filled, so we are going to write 3d10, 4s1, and this is the correct electronic configuration for copper. Do you have any question? Any question? Okay, the last one in this series is the zinc. the zinc has 30 electrons. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d. Of course, we are going to fill the 4s first, and then if we count the number of electrons, we found them to be 20. So we are left with 10 electrons to be placed in the 3d. And now the 3d is completely filled by its electrons. After zinc comes gallium. Gallium, sorry, 31. Gallium has 31 protons, and so it has 31 electrons. So it fills 1s2, 2s2, 2p6, 3s2, 3p6. Of course, it fills 4s2 and then 3d10. Now there is an electron left. Where will it go? Do you know, Yamavi, where does this electron go after 4s?
The 3p orbital.
Yes, excellent. Excellent, يا عمر. ممتاز, excellent. To the 4p1. Excellent, Mavi. We are going to write 4p1. So that's why, by convention, they put the 3 together so that when we write the p, it will come next to the 4s. Now, if you look at gallium, if you have your periodic tables, let me show it to you, but please bring your periodic tables usually with you. If we have, look at this periodic table, you will see that gallium lies below aluminium. It lies below aluminium. You look, you can see this gallium, it lies in the third group below boron, aluminium, and then comes gallium. So when we wrote its electronic configuration, we wrote 4s2 and then 4p1, which means that it is present in group 3. And this is correct. It is present here in group 3. And it is present in the fourth period. This is period 1, this is 2, this is 3, and this is 4. Yes, gallium is present in period 4 and in group 3. Understand, or do you have any question? Okay. Okay. Now we return back to, of course, the electronic configurations. And we said that we draw the electron as an arrow like this or an arrow like that. What does this arrow mean? Now, when an electron is rotating in its subshell or in its orbital, it rotates, as we said, around the nucleus, just like planets. When they rotate around the sun, they take this path. They rotate in circular paths around the sun. So electrons the same. They rotate around the nucleus in the atom, just like the planets rotate around the sun. But also we know that our planets, when they rotate around the sun, they spin. What do we mean by spin? Spin means like go like that. You see? You understand what's spinning? Spinning as if we have a ball and it is spinning. Spinning means it is going round and round around itself. This is spinning, isn't it? So when planets rotate around the sun, our Earth is spinning. That's why we have day and night. That's why we have the sun at a time and the moon at another, because the planet is spinning around itself. It is rotating around the sun, and at the same time, it is spinning around itself. The same happens in case of electrons. Electrons are rotating around the nucleus, and at the same time, they are spinning around itself. The spinning could be clockwise. When an electron spins, the spinning could be clockwise, or it could be anti-clockwise. So whenever we want to express that an electron is rotating clockwise, we do an upward arrow, and the opposite spinning, we do an arrow pointing downward. So these are the spinning of the two electrons. If we draw in a subshell that we have one electron like that, it means that it is spinning in a certain direction. And when we paired this electron, then the two electrons must spin opposite to each other. Also here, we say that they spin opposite to each other in order to minimize the repulsion between them. Because if both of them was spinning together, it means that they are moving all the way together, then the repulsion will be the most. But if one of them spins clockwise and the other spins anti-clockwise, then they will not meet except in a certain point only. And this will minimize the repulsion between the electrons. So always for an atom to be more stable, the electrons must minimize the repulsion. That's why the scientists said that when electrons move in their orbitals, because we said that orbitals are imaginary paths. We don't have a street, we don't have a road at which electrons are moving like cars in a road. No, this is an imaginary path. We imagine that there is a path exactly like planets. There are no roads for planets to move in. They are moving around the sun in a path, but it's not something that you can hold in your hands. Also here, in case of electrons, they are moving around, they are orbiting around the nucleus, and at the same time, they are spinning while they are moving. So we draw one of the arrows upward and the other downward to represent this movement, this spinning of electrons. Okay, you understand, or do you have any question to ask about? Yes, Maggie? Yes.
So they spin in opposite directions, and do they orbit the nucleus in opposite directions too, or in only one direction?
No, it's only one direction, but one of them is spinning clockwise, the other is spinning anti-clockwise. You see?
Okay, thank you.
You're welcome. Any other question? Which party, Hiba, is spinning? Do you want the spinning part? Okay. Okay, what is spinning? You know what's spinning? If you, I'm going to say it in Arabic. تعرفوا حاجة اسمها النحلة الأطفال بيلعبوا بيها؟ Okay. ما تعرفوش النحلة؟ Okay, so when you move this nahla, it spins, isn't it? You will see that it's moving in this way. I'm going, maybe I can see something in the net to show you what's spinning, maybe. Okay, spinning ball, for example. You see, this is spinning, isn't it? Yes, yes, Abdurrahman, that's what I was saying. Yes, excellent. It's like Abdurrahman was saying that our Earth rotates around itself. This is spinning, you see? This is the spinning. To move around, we call this spinning. Okay, Hiba? So one of the electrons is spinning in one direction, the other spins in the opposite direction, because we want to minimize the repulsion between them. If one of them is moving in this direction, the other will move in the opposite direction. You understand me? You understand what's spinning now?
Yes, miss.
Like this way, it is spinning. This is a ball that is spinning. It is spinning in this direction, and the other will be spinning in the opposite direction to minimize the repulsion between the electrons. Okay? Okay. So electrons spin around themselves as they rotate around the sun. We say this rotate around the nucleus, but they spin around themselves. Okay? Now, let me give you an example for ions. I know that the time is getting too small, but I want to finish this part, please. So we said that if I have sodium atom, for example, it has 11 protons, and so it has 11 electrons. So the electronic configuration is 1s2, 2s2, 2p6, 3s1, isn't it? This is the electronic configuration of sodium. We will see that of course, you studied this in O level, but we are going also to study it next in the next chapter, forming bonds. We will see that sodium wants to have the electronic configuration of its nearest inner gas. The nearest inner gas for it is neon. It is 1s2, 2s2, 2p6. And when sodium looks to neon, it sees that neon is very stable. It doesn't make any bonds. It doesn't want to make any bonds. So when it looks at this neon, it will find that its last shell, we say that it is completely filled. It has a full outer shell number of electrons, which are the 8 electrons present in any of the inert gases. So when sodium looks at neon, it says, oh, if only I would lose this electron, I will have the same electronic configuration as neon. And that's what it does. It loses this electron and forms what we call the sodium positive ion plus electron. So what is the electronic configuration of this sodium ion? It will remove this outer electron, and so the sodium ion electronic configuration will be 1s2, 2s2, 2p6. And now it has the same full outer shell number of electrons, just like neon, and it is more stable than when it was like in the sodium atom. So it lost an electron. If we look at an element or a metal present in group 2, like for example magnesium, it has 12 protons, and so it has 12 electrons. So 1s2, 2s2, 2p6, and then 3s2. So also magnesium looks towards neon. If only I can leave these 2 electrons or lose them, I will have the same electronic configuration as neon. And so it will lose these 2 electrons and form the magnesium ion, which has 1s2, 2s2, 2p6. It lost these 2 electrons, and it got the same electronic configuration as neon. Okay, so some of the atoms, like in group 1, 2, and 3, would do the same. They would lose, if we have aluminium, it loses 3 electrons, and also it will have the electronic configuration of the nearest inert gas, which is 1s2, 2s2, 2p6, as it loses 3 of its electrons. But on the other hand, if we look at, for example, fluorine 9, it is 1s2, 2s2, 2p5. Fluorine is present in the 7th period, or in the group 7, because if you count here 2 plus 5, it's 7. So fluorine is present in group 7. It's a halogen. Now, fluorine has 7 electrons in its outermost shell, and it wants to have the electronic configuration of neon. Of course, it's not going to lose, because it only needs only 1 electron to have the same electronic configuration of neon. So fluorine will gain an electron to form what we call the fluoride ion. And if we look to the fluoride ion electronic configuration, it will be 1s2, 2s2, 2p6, and it will have the full outer shell electrons, like neon. It will be more stable. It forms the fluoride ion. And the same in case of oxygen. It has 8 electrons, so 1s2, 2s2, 2p4. So it needs only 2 electrons to complete its octet rule, to complete its outermost shell to be 8 electrons instead of 6. And so it gains 2 electrons and form the oxide ion. And the electronic configuration of the oxide ion is 1s2, 2s2, 2p6. Now it has full outer shell number of electrons, just like neon, and becomes more stable. Okay, understand me, or do you have any question? Okay, now tomorrow, inshallah, we are going